So 2.6, we're going to take a look at variation. In particular, we're going to be constructing functions with variation. There are three types of variation. The reality is there's really only two types, but the third type combines the two types. So we call it a third type of variation. The first type of variation is direct variation. Direct variation has these sort of language components. You might hear that a quantity varies directly with another quantity. The number of hours you spent studying is directly affecting the grade you get on the test. That's a direct variation, okay? As one goes up, the other one goes up. Maybe not in the same amounts, right? But they should be both doing the same thing at the same time. You'll hear the phrase y varies or is directly proportional to, right? The amount of calories you eat is directly proportional to your weight. Now, my calories and your calories and our weights may not quite match, but within your specific body, that's how it works. There's a direct correlation, right? You eat more calories and your weight goes up. That's a direct correlation, directly proportional. There is a K that's going to become involved. K is called the constant of variation, or sometimes called the proportionality constant. And what happens when we have direct variation is we end up with equations that look like this. So the y and the x, if x goes up, y goes up, but maybe not by the same amount. This K tells us how they're actually related specifically. By what amount? So, for example, if you only looked at one component of food, 3,500 calories is 1 pound. Did you know that? It's true. 3,500 calories is 1 pound. So if we were looking at this and we were doing a relationship between calories and pounds, specifically, right, in terms of how your body processes food, if you increase 3,500 calories, we'll say that that's X, then this one would increase by 1 pound, which means my constant of proportionality would be 1 over 3,500. It has to balance out. So it's the corresponding relationship component. K can't be 0. That doesn't make any sense in the context of what we're working at as well. A second type of variation is an inverse variation. Y varies inversely as X. That's a phrase. So it doesn't say directly, it says inversely. Y is inversely proportional to X. And you see that the relationship, instead of being multiplying K and X, is dividing by X. And there's plenty of examples in your everyday life that do this too. So if we're going to focus on, for example, our situation with I'll do the weight one. I was trying to decide which one to do. So I'll do the one with the weight. So if you're talking about the amount that you weigh compared to the amount of exercise that you do, right? Given that everything else stays constant, you're not shifting any of the other things around. If you increase your exercise, you should be decreasing your weight, right? At least that's what we think when we're doing it, right? Otherwise, we're not sure why we're doing it. I mean, maybe we like it, but maybe not. So as you increase one, you decrease the other. That's an inverse relationship that exists, okay? And the last one is called joint variation. And what joint variation does is that it allows you to combine either multiple direct variations or multiple inverse relationships. So the one that's written down here is talking about what happens when we work with it as direct variation. So it says y varies jointly as x and z. Or we'll say y is jointly proportional to x and z. And we see that same direct correlation that we saw before where we have a k, but instead of just k times x, it's k times x times z. So when you hear that word joint, we're going to end up having two things being multiplied times my constant of variation k. So the first things we're going to do is we're just going to change some statements into equations, okay? So we're taking a look at some examples. We're changing statements into equations. The amount of sales tax is directly proportional to the purchase price. I think that you know that, right? You go and you buy a $5 item, you go and you buy a $10 item, the cost of the sales tax is not the same. It's corresponding to the amount of the purchase price. So as we're looking at the language here, the amount of the sales tax means you need a variable representing sales tax. So it will be helpful if you use some sort of variable that makes sense. right? Sales tax, maybe you use an S or maybe you use a T. I'm going to use T for tax. I'm going to use a capital T so that my lowercase t doesn't look like a plus. Is, when we see the word is, it often, not always, but it often translates into an equation, and we are working with equations, so that is a correct statement for what we're doing right now. It says directly proportional. Well, directly proportional, if you'll remember, means we had y equal kx. I've got a multiplication statement here. K is what I don't know. X has to be the other variable. Well, the other variable here described is purchase price. So I'm just going to use P for price. So T equals KP is a reasonable equation for how this is being described. There's other things you could do. We'll be okay if you change some letters around. But choose something that makes sense. On part B, we're looking for these phrases, right? So we saw directly here. On part B, it says jointly. Right? So jointly, if you'll remember, that was the last one we did, said y equals kxz. So we're expecting there to be a k, right? So something is going to equal k, and there's going to be two variables on the right with corresponding to the one variable on the left. So on the left, it says it's the volume of grain that you can have the silo holding. So the volume of grain is V. I'm going to use V for volume anyway. It says it's jointly proportional, or it varies jointly with the height. A good letter for height might be H, yeah. And then things get a little different. It doesn't just say height. It doesn't just say tax. It doesn't just say purchase price. It says something about a square. Square of the radius. So I cannot tell you how many times people get to that point and they do something weird. What does square of the radius mean? It means r squared. Okay, so it doesn't say square root of the radius. That's what usually will happen if somebody makes a mistake, is they confuse the phrase square and square root. So pay careful attention. This says square. It means we're going to take the radius and we're going to square it. And you might actually be familiar with this particular equation. This is an equation for the volume of a cylinder. So that's actually like a real life equation. The first one was too. It just, we don't know the tax rate, or the K right here is not filled in. But those are both equations that happen, and that's where they're coming from. They are direct and joint variations. Okay, we have a couple more, same directions. Reverse directions, what I meant to say. So here we have equations given to us, and it asks us to rewrite the formula in words using the vocabulary of variation. Now you might recognize the equation, and if you change the equation to represent the word that the C or the D or the whatever represents, that's fine. But I'm not expecting that you have to. So first you need to decide, is this a direct, an inverse, or a joint variation on the first one? It is direct. And pi is a number, right? Pi is that number k. K will always be a numerical value. We just don't always know what it is at the outset. Here we do. Okay? So pi doesn't have anything to do with the variation as I describe it. It's my constant of proportionality. So C varies directly with D. That's one of the phrases. So as you go back over here to the first ones we did, you can use any of these phrases. C varies directly as X, or ours was D. C is directly proportional to D. You could use either of those phrases to describe that. Do you know what C and D are? Say it louder, Tiffany.
Circle and diameter.
Very close. It's circumference of the circle, yeah. C is circumference and the D is diameter. If you happened to recognize this and you wrote circle and you wrote diameter in there, that'd be great. But C and D are sufficient. Okay. How about this one? Oh my goodness. We haven't seen one like this yet. So there's a number. That number has to do with the constant of proportionality, so we don't need to worry about it. Okay, it's not part of my description. So we're going to start with the B on the right. B varies. Well, the part on top is a direct variation. The part on bottom is an inverse variation, right? That's how we set them up before. If we had things that are k times x, that was direct. If we had k divided by x, that was inverse. So we simply have to make both statements within the same sentence. So B varies directly with what's on top. So what's on top? With y squared, so with the square of y, much like we had seen it before, right? The r squared, the square of y. And inversely, what's on bottom? Right, with the square root. Make sure that word root shows up. Square root of x. The 2 is the constant of proportionality, much like the pi was in the previous one. The numbered values are not the variation components. All right? They're a constant that's not changing. We don't identify them when we describe it. Any questions on those? Okay, so what we're going to do next is we're going to actually take a word problem statement and we're going to use it to actually do a computation. Okay? So we're basically going to start with problems that look something like A and B here, but we're going to actually use them to do something else. All right, so on 3, what we're finding on 3 is the k value. Okay? So in order to use an equation, we have to have a k value to be able to do so. So as we're taking a look at A, it says h is directly proportional to z. So you're going to pause right there, and you're going to turn that into an equation. So stop for just a second, and I would like for you to write down the corresponding equation that this should correspond to. Okay, what equation did you write down? H equals KZ. Awesome. Did everybody have that? Is that okay? The next thing that will happen is that they will give us H and Z. There's only 3 letters. They gave us 2 of them. We should be able to solve for the third. So H is 210. K is what we're trying to find. And Z is 100. So what would I do then to solve for K? Yeah, I'll divide by 100. You can simplify it either in a simplified fraction form. You can simplify it in a terminating decimal form. Either one actually work just fine for this. So you can either write down from here that K is equal to 2.1. That's a very nice one. Or you could have written that K is equal to 21 over 10. That's its terminating, or the simplified decimal form and fractional forms. But what we want to actually do is not only find the constant of variation, which we just did, we also want to construct the function. Now, we constructed the function initially, but we didn't know K, right? But now we do know K. So we can actually create the function specifically. H is equal, I'm going to use the decimal form, to 2.1 Z. That's the function that the problem is asking us to construct. The function that actually identifies what is K. Okay, let's try this one. Start with the equation generally written with the K in it. This one's a little bit trickier than the last one, so take a second to take a look. P varies directly as the cube root of W. What would that equation with the K in it look like? Write it down, and then we'll check and see if you're on the right track. What equation did you write? I hope it started with P equals, yeah? Awesome. Now what? K cube root of W, right? Yes. Awesome. That's a good first start. Because I'll tell you what, if you get stuck at that point, everything else will fall apart. It's a good place to be. All right. Good. So we're on a good track. And then they give us some values, right? They tell us what P and W are. P is 6, W is 8. So P is 6, W is 8. So what is the cube root of 8? 2. And if I divide by 2, what will k be? What is it? 3. K's 3. Okay, so we've done we've done more than half the directions, but like they only give us 2 pieces. We did the first piece. The last piece, writing the equation. What was my equation full out now? P equals 3 cube root of W. Is that okay? Because we're going to take it one step further. What we're doing in these last sets of problems is exactly what we just did. But then we're going to use that equation we just found to find a quantity. So you'll notice that it has that first piece of information about how the relationship exists. It has this piece of information where it identifies 2 pieces, and you can find k. And then it asks you a question about what happens when a certain value is used for one of your variables. Okay? There are 3 steps, and they are written just right there. Those are the 3 steps. So the first step is to write that general equation. And you guys have done it now. I think we're at about 6 times. So what is the general equation that this is setting up? Y is inversely proportional to z. What does that look like? Y equals what? K over z. Inversely puts the variable in the denominator. Y equals k over z. Okay, everybody good with that? So that's sort of step 1. I'll label them just so you can see them this time. Step 2 is that I'm going to use the values where y is 6 and z is square root 75. So y is 6 and z is the square root of 75. That does allow me to find k, correct? It does. What would I need to do to find k here? Multiply by the square root of 75, which we're going to have to simplify at some point, by the way. We haven't done it yet, but we will. So I have k all by itself now, which is what I was going for. And I have 6 square roots of 75. But we want our k value in its simplified, most simplified form. And square root of 75 is not simplified. So we've done a fair bit with simplifying radicals. What do I do with my 75? I break it down. So what will 75 break down into? Okay, so you can do, what did you say? 3 and 25, that's one of them. Yeah, that's one of the options. And then 25 would be 5 and 5. You might have broken it down to 5 and 15. Was that what you were trying to tell me? Huh? 5. You were telling me the final answer. Thanks, David. Sorry, you're correct. So I have 2 pieces, this 5 and the 5, that will come out with my 6. So I have 6 times, there's my 5, and then the square root of 3 that remains. So my k value when combined, this will give me 30. Hang on. Come on. There we go. So my k value is 30 square root 3. Is that good for everybody? 30 square root 3? Okay. So the final result of that step 2 is to write the equation with k evaluated in. So that is y equals 30 square root 3 over z. Good? All that so far is just like we did in the last two problems. And then step 3 is to take the new information that they give us down here. So where they told us that the y is the square root, the z is the square root of 12, and we're going to put square root of 12 in for z here. Okay? And we're going to correspondingly then solve for y. So I have y equals, I have 30 square root 3 over now the square root of 12. Square root of 12 is not in a simplified form either, much like the 75 wasn't. So if I were to break 12 down, I would get 4 and 3 or 2, 2 and 3. And the 2's would come out, right? So as I'm simplifying this expression, I end up with 2 square root 3 from the square root of 12 here. And what do you notice about my square root of 3's? They do. They cancel. Not only that, but 30 divided by 2 is also very nice, and it is a 15. So at the very end of this type of a problem, we are actually solving for y. We have an actual numerical value coming out of our equation. But it all leads up to what's actually happening with problem number 5. So problem number 5 combines a bunch of the different pieces that we've looked at. If y is directly proportional to the square root of u and inversely proportional to the square of v, we saw that kind of language before, right? That's step 1. All of this is step 1 for finding the equation. And then they tell us some information. And y equals 7 when u is 9 and v is 6. That's step 2. That's going to allow us to find k. Then what happens when u is 4 and v is 8? And that's step 3. So everybody see the 3 steps. It's really important to recognize there's 3 distinctly different things you're doing. Yeah? Okay, so the first one here, the writing of the equation, is kind of messy, right? It's kind of a wordy one. It says y. So y is my variable. So when it talks about being directly proportional to the square root of u, what does that mean? There's a k in front of here. I'm just going to do that for now. What does it mean to be directly proportional to the square root of u? Where is it going to be? Top or bottom? It's going to be on the top because it's directly proportional, right? Square root of u would look like the square root of u like that, right? Okay. Inversely proportional. When I see that word inversely, it means it's going to go on bottom. And it says the square of v, so that's actually v squared. Okay, that's step 1. We got to get the equation written in right to start with, or we can't proceed. Step 2 gives me 3 variables, because I have 3 variables in this problem, which will allow me to solve for k, which is the constant. It's a number. So it tells me that y is 7. K is what I'm looking for. U is 9, so I have the square root of 9. And v is 6, so I have 6 squared on bottom. Is all that all right? Okay, we have a couple of different things we could do to start for simplifying. What would you like to simplify first? Square root of 9. That's what I'd want to do too. What's the square root of 9? 3. So this is k times 3 on top. There's no reason to cram it in here. Let's move over. K times 3 on top. How about we do the bottom at the same time? What's the bottom? 36. You could do a couple of things. You could multiply the 36 to the other side and then divide by 3. That would be fine. You could also look at the k times the 3. I should probably put a dot in here just to remind us that they are multiplied. And you could simplify the 3 and the 36 here. It doesn't make any difference. How about we simplify the 3 and the 36? 3 and 36 both divide by 3, right? And so I get a 12 in the denominator. So this one gives me a 12 here and a 1 here. So I end up with y equals k over 12. Oh, I didn't. Yeah, my 7 left me. I just didn't rewrite it. So sorry. I was about to say that's not right. There we go. 7 equals k over 12. Then I would, multiply by 12. So what is 7 times 12? 84. Did you learn your multiplication tables to 12s? I didn't, but my children have. So maybe y'all have too. You're somewhere in between me and my kids at this point. So multiplications by 12s. 84. K is 84. So what's my actual equation that I've got now that I can pull all the pieces together? Excellent. Okay, does that look okay for step 2? Yeah? Cool. And then step 3 says I have u is 4, v is 8, and I need to solve for y. So y equals 84. I have the square root of u, so the square root of 4, over v squared, which is 8 squared. Okay, so I now have 84 on top. The square root of 4 is 2, and 8 squared is 68. You're welcome to either multiply the 84 and the 2 together and then divide by the 68, or you're welcome to divide out the 2 and the 68, make them smaller first. It really doesn't matter.
64.
Oh, I wrote it wrong. 64. That'll make a difference. The 2 and the 64, you're welcome to reduce those first before you multiply the 84. It doesn't matter. You can go in any order that you would like. As you simplify this, it's messy. It's not a pretty simplification. It will end up giving you 21 over 8 if you write it in fractional form. It actually has a terminating decimal as well if you prefer that. It's 2.625. That is crammed in unnecessarily. 2.625. So either of those are fine. When you get to the end of one of these problems, and even actually in the middle as well, while I'm telling you you're welcome to use decimals or fractions, remember the types of decimals and fractions I'm referring to. If this answer over here had given you something that was like a repeating decimal, we're not going to write it in a repeating decimal form. That's not a simplified, clean way to write it, okay? If we had ended up with this fraction, but it wasn't reduced, like we had done some of the reducing, but I still had more reducing to do, it wouldn't be finished either. We would want to make sure it gets finished. And heavens to Betsy, please don't use mixed numbers. It's not going to be nice in any way, shape, or form. The one other thing that you're going to see in your homework, just to preface you this with, is there's going to be word problems with context. So they'll say something like my example with the calories, right? They'll create an equation where you've actually got not just letters going on, but words associated with those letters that have physical context. And then you'll be solving for things. They're not any different. Pick a letter and use it. You'll be just fine. But there's some of them that have that nuance to them. All right, so homework for next Tuesday. You have sections 2.5 and 2.6, and then we are going to do the review on Tuesday, all right? All right, have a great week. Enjoy your fall break.